Very much. So I'd like to first thank the organizers for the opportunity to give this talk today. And I would like to also emphasize that the results I'm showing today are made in teamwork. So I owe thanks to the members of my ERC group, some of whom will be giving their own talks later today. So today I'm going to talk about young eruptive stars, and this topic is interesting not only because the eruptive phenomenon may be very widespread during star formation, but also because the temporarily increased luminosity of these objects allows us to study certain aspects or certain details of the star formation process that would otherwise be inaccessible. So we may learn especially interesting things if we take sharp enough images. So to give you a little bit of an introduction, this sketch shows the time evolution, the time dependence of the accretion rate from the circumstellar disk onto the young star, the forming star. You can see that protostellar accretion and disk evolution is not a smooth process. It's not something that evolves slowly over hundreds of thousands of years or even millions of years, but it is in reality episodic. So you can see these very sharp, very strong peaks in the accretion rate when the accretion rate increases by several orders of magnitude. You can see in this sketch that these peaks are called Fjord and XOR outbursts. Fjords and XORs are classes of variable stars, collectively known as young eruptive stars. And in this talk, I'm going to focus on the Fjords. This class is named after the prototype Fu Orionis. And it was defined first in 1971 by Victor Ambartsumian. And at that time, this class contained two objects, Fu Orionis and V1057 Cygni. Since then, of course, many more Fjord-type objects have been discovered. And there are also very nice reviews, a series of papers, if you need further reading. The latest one just appeared on AstroPH a couple of weeks ago. But for many, many years, the review to cite in this field was the seminal paper of Lee Hartman and Scott Kenyon from 1996. And that paper contains these light curves. So these are optical light curves of the three classical Fjords. And I made a little experiment and complemented these light curves with the data obtained since then. And this is what they look like now. So there are many interesting things happening with these stars. And if you're curious about the first two, those in Cygnus, you can check the papers I'm doing with my student, Zsófia Szabó. And it is also very interesting to look at the bottom one, the prototype Fu Orionis, which has been in outburst and only slowly fading for almost 90 years now. So if you are curious about what a disk of this object looks like at high resolution, listen to the talk of my colleague Claire, who will talk. I will show us some very nice MATIS results about it in about half an hour. So young eruptive stars are basically the observational evidences of episodic accretion. The accretion rate in these objects increases quite suddenly in a few months or in a few years by several orders of magnitude. It can reach up to 10⁻⁴ solar masses per year. And as a consequence, their bolometric luminosity also increases from a few solar luminosities to a few 10 or a few hundreds of solar luminosities. And their light curves, as observed at optical or infrared wavelengths, shows a brightening by 3 to 5 magnitudes. And in some cases, they also illuminate nice reflection nebulae. For comparison, a change in the total solar irradiance is less than 1%. And even T-Tauri stars, regular T-Tauri stars, only vary by 0.1 to 1 magnitude. So you can imagine that such a large brightness change, 3 to 5 magnitudes, may have a substantial effect on the disk. But how do outbursts affect different properties of the disk? Can they affect the disk structure, mineralogy, or chemistry? If you remember, I mentioned that the peak accretion rate is about 10⁻⁴ solar masses per year. So if a typical Fjord outburst lasts for a century, a star may collect as much as 0.01 solar mass or 10 Jupiter mass in a single eruption. So outbursting disks must be very large and very massive, right? With interesting substructures. But do observations confirm this? And why do young stars, or more precisely their disks, erupt at all? Do they become unstable in a viscous thermal, gravitational, or magnetorotational way? Are they perturbed by a substellar or stellar companion? Do they capture a cloudlet or collide with a streamer? how did they finish the outbursts and how they are replenished afterwards for a repeat performance. And the most interesting question of all, do all young sun-like stars go through these eruptive phases? To answer this question, we need to find out whether the disks of young eruptive stars are in any way different from the disks of normal non-eruptive young stars. So motivated by this, we made an ALMA survey of the disks of fjord-type objects. We targeted 10 of these at 1.3 millimeter continuum with a sub-arcsecond resolution, so our synthesized beam was about 0.15 arcsecond. We used a combination of two 12-meter array configurations and a 7-meter array to properly sample emission at all spatial scales. So you can see our 1.3 millimeter maps of these 10 objects here. And I will talk about this sample as an ensemble, but if you are, again, curious about individual objects, you can listen to the talks of my colleague Fernando will talk after me about one of these objects, L1559RS5. It's a very interesting binary system. And tomorrow, my other colleague Peter will talk about V900 MON, showing some very nice MATIS results on that one. So what did we do with these ALMA images? Well, we modeled them. We first used an analytical disk model that had an intensity profile, which is a power law with an exponential taper, and we fitted this in a visibility space. But of course, disks may be optically thick even at millimeter wavelengths. So to get a proper estimate of the mass of the disk, we need to use radiative transfer that properly takes into account optical depth effects by ray tracing. So that's what we did with RADMC 3D, and that we fitted in the image space. So I'm not going to show all the results, but just two examples. This is one of the lower mass disks. You can see the parameters that we got with the two different models, and the geometrical disk parameters like the radius, inclination, or position angle are quite similar between the two types of models, especially for this one, which is very well resolved. And then there's another example, one of the higher mass disks. Again, the geometrical parameters are quite similar between the two different models. But important result of this modeling is actually that our radiative transfer model gives us proper disk masses in addition to the characteristic disk radii. And we collected these parameters from the literature also for other fjords and for normal class 2, class 1 disks that were modeled in the exact same way as we did our sample. And what you can see here on the left-hand side is that fjords, so the orange and green points, display systematically higher disk mass and smaller disk radius than the normal non-outbursting stars. And the histograms and the cumulative distributions show the same, basically. So fjord disks are somehow different to begin with from the general disk population, or the outbursts make them somehow special. They're also a bit puffed up. Their scale heights are typically quite high. Their radii are at the low end. I already mentioned that. And the disk masses actually show a quite large spread, and some of them are very low mass. So there are a few % of solar mass, which is actually comparable to the total mass collected in one fjord outburst. So it's a question, how can these disks erupt? Are we just so lucky that we see the last outburst these disks can produce, or maybe they will be replenished later, but that's very difficult to observationally check. But actually, most of them are rather high mass, and we started wondering whether they may be gravitationally unstable. That's a very interesting question, because gravitational instability is one of the proposed trigger mechanisms for fjord outbursts. And we can check that if we know the stellar mass. One of the usual criteria for gravitational instability is that the disk mass should be more than 10% of the stellar mass. And this criterion is actually satisfied by about 2/3 of our sample. So most of the disks, fjord disks that we studied may be gravitationally unstable. It's still an open question whether we should see with ALMA substructures in the disk due to gravitational fragmentation, for example. There are numerical studies that predict that we should see such substructures like those I'm showing here by Robin Dole. But there are other numerical studies, for example, by Eduard Vorobiev, who predict that the outbursts, given enough time, would smear out these substructures by heating and expanding the disk. In our specific case, of course, it is possible that we simply don't see this because we are not sensitive enough or we don't have enough spatial resolution, because unfortunately, most of these objects are quite distant, so they are around 1 kiloparsec or even farther away. So just to summarize, I was talking about young eruptive stars, objects that show accretion-related outbursts. These eruptions are so far overlooked, but potentially a very important fundamental phase of the formation of sun-like stars, and they overlap in time with planet formation. I showed results from our research program characterizing these stars and disks at high spatial resolution. And our results show that the disks of young eruptive stars, especially those of fjords, are special. They seem to be smaller and more massive than normal non-eruptive stars, and with larger scale heights, and they are potentially gravitationally unstable. But we've also seen examples for low mass disks around these objects, so there may be no single theory that explains all of them. So of course, more observations and more modeling are necessary, so we will keep working on it. Thank you very much.
Thank you, Ágnes. Any questions? Ágnes? Yeah, we have one question over there.
Thank you. Nice talk. You mentioned for your radial transfer modeling that the disks are puffed up. Is that consistent with viscous heating in the midplane, and therefore the scalar is increased, or is even more needed to explain this?
I think that could be possible. I mean, we didn't really check it numerically, but I can imagine that because of the heating of the midplane, this is not a surprising result. Yes.
Mm-hmm. Thanks.
Yeah, one more.
Thanks. Do you have any sense as to whether or not the physical parameters you've derived for the disk features might be biased by the fact that the sources are at the limit of being resolved, and so you might be struggling to measure the high spatial frequency content of the image?
I think so. So my suspicion is that if they were closer, we would probably see substructures. So that's my suspicion. There are some objects which are quite close by, and yeah, I know from archival ALMA observations of EX Lupi, which is the prototype of the other class of young star objects that has this gap and ring structure. We do see substructures in L1559 RS5, which is a closest object in our sample at 150 parsec in Taurus. So I think the lack of substructures is just because we barely resolve them. But these bulk parameters like characteristic radius and mass, I think that's fine. That should be fine.
Any more questions? One question I would have is like, are you planning maybe to also explore in shorter wavelengths to go to near interferometry and try to combine, because also these processes are happening really close to the star? So I was wondering if you have more data on that.
Yes. So in a couple of minutes there will be, and also tomorrow there will be talks for some of these objects for FURI and for V900 MON, which we managed to measure with the MATIS. Unfortunately, because of these stars' large distance, and also because some of them are quite deeply embedded, so they are actually they're bright in the far infrared and millimeter, but they're much fainter in near infrared or optical. There are only a few of them which are suitable for infrared interferometry. So we are trying our best, but better limiting magnitudes would help us.
Okay, perfect. Thank you. So if there are no further questions, let's thank Ágnes again.